Welcome to the Explainer. So let's talk about how to solve the biggest problems in the world. Do you build one single massive army to do your bidding? Or do you create a council of powerful leaders who can work together? Because in the world of supercomputing, that's the fundamental difference between two titans, CUDA and MPI.
But first, why do we even need these superpowers? Well, it's because the problems we're trying to solve now, we're talking training AI, modeling climate change, discovering new drugs, they involve just an unbelievable amount of data. Your standard computer, trying to chip away at that one step at a time, it wouldn't just be slow, it would literally take centuries to get an answer. It's just not possible.
And this right here shows you why. On the left, you've got the old way, sequential computing. It's like a single checkout line at the grocery store. Slow, one person at a time. To deal with the mountains of data we have today, we need to think in parallel. That's what you see on the right. It's like opening up thousands of checkout lanes all at once. This one idea, going parallel, is the key to everything we're about to talk about.
Okay, let's dive into our first superpower, CUDA. This is the one army approach, and it's all about unlocking the insane power hiding inside a single computer. So what is CUDA? Well, the fancy name is Compute Unified Device Architecture. It's a platform from NVIDIA, but what it really is a key that lets us open up the graphics card in your computer, the GPU, and use it for, well, anything. It takes a device built to make video games look pretty and turns it into a general-purpose, number-crunching beast.
And I love this analogy because it's so perfect. Think of your computer's main processor, the CPU, as the general. The GPU, then, is its enormous, highly disciplined army, made up of thousands and thousands of tiny soldiers called threads. The general, the CPU, gives a single command, and every single one of those soldiers executes that exact same order at the exact same time. It's massively efficient.
And here's the battle plan in action. It's really a three-step dance. First, the general, our CPU, sends all the data, all the supplies, over to the army on the GPU. Step 2, the general gives the big order by launching something called a kernel. That's the main task. And finally, once the army's done, the results are copied back from the GPU to the CPU for inspection. Simple, right? Now that word, kernel, is absolutely crucial. It's just a single function, a single piece of code. But when the general launches it, that one program is run by every single thread in the army at the same time. This is a model called SPMD, Single Program, Multiple Data. One order, thousands of soldiers, each working on their own little piece of the puzzle. But what if your problem is so big that even a massive army inside one computer isn't enough? What if you need to coordinate entire countries to solve it? Well, that's where our second superpower, MPI, comes into play. So, meet MPI, the Message Passing Interface. Now, the first thing to get straight is that MPI isn't a programming language. It's more like a diplomatic handbook, a set of rules of engagement. It's the official protocol that allows completely separate computers, we call them processes, to talk to each other and work together on one shared problem.
So, if CUDA is one general commanding an army, MPI is a council of independent leaders. Each leader or process is its own powerful computer running its own program. And here's the key difference. They don't share a brain. They don't share memory. The only way they can solve the problem is by talking to each other, by sending messages back and forth to coordinate their strategy.
When an MPI program starts, it's basically like the council is called to session. MPI init kicks the whole thing off. Then, right away, each member of the council needs to figure out two things. First, how many of us are there in total? That's MPI com size. And second, who am I? What's my unique ID in this group? That's MPI com rank. And it's super important so that, say, rank 0 can act as the main coordinator. And on this council, communication is everything. It happens in two main flavors. You've got point-to-point, which is like one leader passing a private note directly to another leader, and then you have collective communication, which is more like one leader standing up and shouting an announcement to the entire room, making sure everyone gets the exact same information at the same time. Okay, so we've met the single machine army and the multi-machine council. Now it's time for the showdown. Let's put them head-to-head and really see what makes them tick. This table just lays it all out perfectly. At the end of the day, CUDA is all about scaling up, cramming as much parallel power as you possibly can into one machine. It uses a shared memory model inside that GPU, which makes it absolutely amazing for problems like image processing, where you're doing the same simple thing to millions of pixels.
MPI, on the other hand, is about scaling out. It distributes the problem across many machines, each with its own private memory. It's built for those truly enormous problems that are just too big for any one computer on Earth to handle.
So where does this all leave us? What does the future look like? Let's take a quick look at how these two superpowers are literally shaping our world right now.
Look, here's the bottom line. This isn't just academic. Without these two ways of thinking in parallel, so much of our modern world just wouldn't exist. The artificial intelligence on your phone, the mind-bending medical discoveries coming from things like protein folding, even the weather forecast you checked this morning, all of it is built on the backs of these technologies.
And you can see them in their natural habitats, right? CUDA, with its internal armies, is the undisputed king of AI, machine learning, and graphics. MPI is the diplomatic language that connects the planet's biggest supercomputers for things like nuclear simulations. But, and this is the really cool part, the most powerful systems in the world combine them. They use a hybrid approach. MPI acts as the high-level council, coordinating between hundreds of computers, and then each of those computers uses CUDA as its own internal army to blitz through its piece of the work. It's the best of both worlds.
And all of this brings us to one final big question. As our problems get even more complicated and our hunger for computing grows, which philosophy is going to win out? Will the future belong to engineering ever bigger armies on a single sliver of silicon? Or will it be about building larger and larger global councils of collaborating machines? The truth is, the answer is probably both. And that answer is going to define the next wave of human discovery.